talking about this webinar, okay, first we will talk about the ANSYS. Okay, like what is ANSYS and why we use the ANSYS for the simulation part. So for the simulation part, the ANSYS is there. Okay, but whenever we heard about the ANSYS or whenever we heard about the simulation, the first questions that comes in our mind, which is why do we simulate? Okay, we have to do the simulations before actual prototyping or before actual physical designs. We have to do first the simulations. Okay, so what is the requirement of that simulations? Okay, it is necessary to do the simulation. Why it is necessary? Okay, so first of all, the first reason is like the help to meet the product code regulations. Okay, these are the product code regulations. Are there like any of the product you want to design? Okay, whether it is motor, whether it is any of the electric vehicles, or you can say any type of electric vehicle or combustion vehicle. Okay, so government has some standard of it, some product code regulations are there. Okay, so that regulations we have to meet first whenever we design that product and whenever we want to use that product in the market. Okay, so make sure that the whatever the product codes are there, okay, that designed by the government, okay, or that designed by the particular government body, okay, that should be regulated by your product. Then we have to increase the efficiency and the performance reliability of your product. Okay, like if you have to, suppose you are taking like an example of electric vehicles. Okay, now we have to increase the product performance. Product performance means we have to increase the range of an electric vehicle. Suppose right now an electric vehicle which has range around 300 kilometer, okay, in one charge. Okay, so we have to increase the performance means we have to make the range better. Okay, or for the same tendency, like different ways are there to increase the product performance. It is not like a only one way that you can for the electric vehicle. It is not only about the range part. Okay, so you can develop the new battery or you can use the efficient battery. Okay, so your automatically your range is getting better. Okay, so there are the different ways you have to pick to like increase the performance and the reliability of your product. Okay, then find out the root cause failure. Okay, so if any product is there, okay, so suppose electric motor is there. So electric motor is depends on the electromagnetic parameters, as well as because of the electromagnetic parameters, because of the electromagnetic losses, the heat is getting generated. So to counter that heat part, we have to design the cooling strategy also. Okay, so we have to check for the thermal performance, whether thermal performance, whether whatever the temperature is that should be sufficient or not. Okay, and then we have to check in the electric motor the rotor is rotating. Okay, so because of that rotation, some stress is getting generated on the rotor part or on the magnet part. Okay, so that stress value we have to check also, like the reliability of those particular physical components we have to check. Okay, so whenever that particular product is going to be failed, okay, so we have to know like at which particular point it is going to fail. Okay, it is failed by electromagnetic parameters, it is failed by thermal parameters, or it is failed by the structural parameter. If it is failed by the structural parameter, then we are morely looking for the materials change, or we can pick the better materials. Okay, whatever the failures are there. Okay. So regarding that, we have to pick the root cause failure. Then our aim is like to reduce the time and the cost of product development. Suppose if you take any product, okay, you want to design the product and you want to get that product in the market. Okay, so you have to, in the minimal time, you have to enter that product into the market. Okay, and the cost of whatever the cost is going to be there for the development of this particular product. Okay, that should be minimum. So it makes sure that the affordability is better. Okay, so suppose electric vehicle is there, if the cost is minimum, then more people will buy the electric vehicles. Okay, so like this is the scenario is there. Then we are looking for like a this is the broadest portfolio of ANSYS, like what ANSYS has particularly in the simulation industry. Okay, so it has the academic packages are there, which includes the structural product, fluid product, and the electronics product. In the electronics, both low frequency and high frequency products are there. Next, the materials products are there for the research and development of any of the materials, or you want to use any of the new materials in your simulations. Then connect tools for the optimization part. Then for the optical phenomena. Okay, there are the optical tools are also there. Then for the embedded softwares. Okay, so for the embedded tools, we have embedded skate tools are there, and for the system simulation. Now, what is the system simulation is there? Now you can see like the electric vehicle is there. Okay, in the electric vehicle, it is not like a electric part or mechanical part. All the parts are there. Like in the electric vehicles, structural part also there, fluids, parts are also there. On the thermal parts, you can say the electronics part and electrical parts are also there. Okay, so you have to check the complete system simulations. Like whenever you build the electric vehicles, whenever you run the electric vehicles on the road, okay, so that electric vehicles might be failed because of the structural point of view, because of the any of the software issue or any of the thermal issue of the any of the product or any of the electronic issue like wiring harness or other the issues are there. Okay, so for the system in the system simulations in the twin builder too, you can see like how your electric machine behaves whenever you drive that particular electric vehicles on the road, how the particular electric vehicle works. Okay, that you can see in the twin builder environment. Then for the semiconductor tools are also there. Okay, then ANSYS has a cloud tools, ANSYS cloud is there. And for the autonomous vehicle simulations, it is a AV simulation part, which is AV accelerate, and which is basically check the like the autonomous vehicles, like in the autonomous vehicles, you can see like the self-driving vehicles. Okay, so it is checking the how much the autonomous or how much the ADAS it has, like level 1, level 2, level 3, like this. Okay. Now we'll see why top auto OEM, whatever the automotive industry OEMs are there or top tier industries, okay, use ANSYS for their success. Okay, why they are using? Because they have to make their organization profitable. Okay, for the rapid decision making. Okay, and the best part about the ANSYS is that it has a multi-physics capability. Means complete multi-physics you can do for your any of the product. Okay, the complete multi-physics simulations you can do by using the ANSYS tools. Okay. Okay. So whenever you talk about the automotive industry, okay, so in the automotive industry, ANSYS is more focused on the three parts. Okay, the three parts, like the three areas you can say, or the three main pillars are there, which is the electromobility. Okay, then the software defined vehicles, and then the ADAS and autonomy. ADAS and autonomy means the autonomic vehicles, the self-driving vehicles, like you know about the Tesla Motors. Okay, they are building the self-driving vehicles, the electric vehicle and the self-driving vehicles they are building. Okay. And in the electromobility, what is the system integrations? We have to develop the battery and battery management system. Okay, the electric machines, to optimize electric machines, then the power electronics, electric box, and the fuel cell also. Some electric vehicles are the fuel cell electric vehicles are also there in the market. And then the software defined vehicles. So which is important whenever you have to define the complete architecture of it. Okay, that is defined based on the embedded software. Okay, so that is software defined vehicles. Then the ADAS and autonomy to communicate the data between the two vehicles. Okay, like vehicles. Okay, so driver is not there. Okay, so if the driver is not there, so whenever the two autonomous vehicles are running on the road, okay, so like that two vehicles are going to be connected with each other. The connected means they are sharing the data. Okay, so that's why they know like when to turn and like what is the distance between two vehicles. So that ought should be there because to prevent the like the road accident. So that communications will be important. And then the complete vehicle development. The vehicle development, the complete vehicle development is like a physical development, you can say, which includes the structural reliability, crash safety analysis. We have to check also. Like in the India, the NCAP rating is there. Okay, so that NCAP rating is based upon the crash analysis. Then the aerodynamics analysis is there. Okay, so it is like a drag coefficient. It is based upon the drag coefficient. Like lesser the drag coefficient, the more efficient the vehicle is there. Okay, like the more force is not required for the vehicle to push forward. So it is like aerodynamics analysis, thermal analysis, and then the optimization and the exterior as well as the interior lighting design and the reflections. Like the lighting phenomenon also important. And whenever the communication part is there, that EMI EMC also getting in the picture. Okay. Whenever we talk about the autonomous industry, okay, the automotive industry, okay, the main example is like the ROI is there. Okay, the ROI, whenever you are using the simulations, what is the benefit of the simulations? Okay, like whenever we use any of the simulation software, okay, so for that simulation software, the return on investment, like how much we invest for that simulation software, okay, and how much we will get from return. Okay, so like the prototyping tooling, prototyping materials, testing parts, like any of the test you can do. Like if you want to do the crash testing for this particular material, you can do the crash testing in the software first, can collect the results, and then you can, like, whenever you go for the optimum design, okay, whenever you achieve that optimum design by using the software itself, okay, then you can go for the actual prototype. Okay, then you can check the results or you can validate the results. That phase is called as a validation. You can validate the results with the whatever the results are there, physical results as well as your software results. How much the efficiency or how much the correction is there between these two results. If the correction is there, then because if after the one try, if you want to modify that design, okay, then there is no use of whenever you do the physical prototype. Okay. And to improve the speed and the quality of an automotive innovations, okay, like decrease time to market, okay, like after each year, or you can say like after each year the new vehicles are there, after each month, like in the each month the new vehicle is comes into the market, okay, like it is based upon the digital engineering, and this digital engineering is based upon the two factors, okay, like the software defined vehicles and the electrified powertrain. Okay, these are the modern trends you can see, like software defined vehicles, ADAS, electrified powertrain, and the full vehicle development. This is full vehicle development means the complete architecture of it, the physical architecture. Okay. And whenever you talk about the challenges, okay, like whenever the automotive industry is there, we have to talk about the challenge. What are the challenges are there? Right now, the electric range is the one challenge, okay, for adoption of the electric vehicles. Okay. So if the electric vehicle right now in the India, it is supposed like the car which gets the more electric range, which is about 350 to 400 kilometers. Okay. Like you have the Tata car, is the Tata Nexon is there, I think, which gives the 350 to 400 kilometer range. Okay, so if we have to increase the adoption rate, what we have to do? We have to increase that particular range. Okay, or for the increase of the range, what are the different parameters or what are the different strategies are there to increase that range? Okay, like you can increase the power density of the battery. Okay, or you can decrease the size of the battery. Size means the weight of the battery. Okay, or the complete vehicle weight you can decrease. Okay, like these are the different strategies are there. Then the fuel economy. Okay, like if you talk about the internal combustion engine, the fuel economy is there. We can give the better mileage. Okay, based upon the power and the speeds. Okay. Then the pollution, the pollutant emissions are there right now in the India. The E20 fuel, E30 fuel, like this, the ethanol fuel is there to give the more adoption and to restrict the pollutant emissions. Okay, and then the crash ratings are there. Like in India, the NCAP rating is there. In the Europe, that Euro NCAP is there. So it's like a 5-star, 4-star, 3-star rating, which is based upon the safety parameter. Okay, and then obviously the cost parameter is also there. Okay. By using the simulations, what we actually achieve, okay, we achieve the 3x acceleration of the simulation product. 3x acceleration means in whatever the time is there. Suppose in the one company is there, okay, which are developing the automotive industry or automotive vehicles. Any of the vehicle you can take. Okay, suppose that particular companies develop one vehicle per year. Okay, now what happened by using the simulations? Okay, they can develop the 3 new motors or the 3 new vehicles per year. Okay, like their productivity of their or the productivity of, you can say, like the overall productivity is going to be increased. So first they, like previously they develop only the one electric vehicles or the one vehicle per year. Now by in the simulation software, okay, they save their time, and with that save time they develop the 3 more new vehicles. Okay, and the design cycle time reduction, because the time reduction is there, they're going to more time for the new vehicles, and they can develop the new vehicles or updated the whatever the existing designs are there, they can update this existing design, and they can try for the weight reduction also. If the weight reduction is there, the more productivity or more efficiency you will get from your machine. Okay, or machine or any of the electric vehicles you can take. And in the vehicle engineering part, what are the different areas are there, or the critical areas you can say? First is the exterior part. In the exterior, the aerodynamics, overall the exterior part is there. Okay, the aeroacoustic, thermal management, the interior parts are also there. Okay, so that each part we will discuss. Chassis, powertrain, and then the electrical. In the electrical, you can see the electric vehicles compartment is also here. Okay, and in the exterior simulation capabilities, okay, exterior external aerodynamics, okay, the air acoustic is there. Because of that, wind the sound is also getting generated. Okay, so we have to measure that sound also, like how much the decibel that sound is there. Thermal management, okay, then water management and soiling. Okay, and the soiling means like whenever you can see like the 4x4 vehicles are there, they can run on the mods, okay, run in the mods. And then the structural integrity is there for the crash part, or you can say like hello. And the external aerodynamics is there. Okay, what are the challenges? The drag reduction. The first challenge is there whenever you are talking about the aerodynamics. It is the reduction of the drag. To minimize the force that the vehicle required to push forward. Okay, that force we have to reduce. Okay, the reduction of force means the drag reduction. Drag reduction means the more power you will get from your vehicles. Okay, like these are the external aerodynamics one. Okay. Like this, you can use the external aerodynamics. Like in the fluent, you can do the vehicles part. Okay, and then you can flow the air from it, and then you can check it. Okay. The aeroacoustic part is also there because of the air. Okay, because of the air, the noise sources are there. Air is like a noise sources. Whenever that air is stuck in any of the electric vehicles part or the exterior part, the sound is getting generated. Okay, so it is based upon the speed is there, how much the velocity of your vehicle. Okay, and it is based upon how much the like a particular air temperature at that particular point. Okay, that is also comes in picture. In the thermal management, like in the internal combustion engine, the cooling systems are there. In the electric vehicles also, the battery cooling systems are there. Okay, for the cooling of the battery and cooling of the electric machines. Okay, then the water management and the soiling. Like in the picture, you can see like actually where you want to use your electric vehicles. Okay, that is more things about this, the water management and the soiling. Like if you want to use your electric vehicles on the highways, or if you want to electric vehicles in the desert areas, or any of the like the in the like the 4x4 vehicles are there. Okay, like they are using in the mostly desert area and the where the mud is there, like the forest regions. Then the structural integrity is most important. Okay, so whenever you talk about the safety, we are talking about the structural integrity. Okay, how much the structural integrity that it has. Okay, like if you give the ratings of the any of the Tata cars or Mahindra cars. Okay, we are basically see like how much the structural integrity it has, how much the structural capability it has. Okay? And that the NCAP testing is there in India. And then the interiors are also you can design, or interior also you can check by using the simulations like climate control, HVAC system, your AC system, then cabin acoustics. Okay, now you can see this cabin acoustic, like whenever you close the mirror, the sound is different. Okay, and whenever you open the mirror, okay, and whenever you're driving the vehicle, suppose for the 50 kilometer per hour, and whenever you open the windows, okay, you can see like the more noise is there. Okay, so that because of the noise is there because of the acoustic parameter of the airs. Then the crash and safety again. Okay, and then the ergonomics are there. Okay, how beautifully you can arrange the ergonomics inside the vehicle. So the climate control system, which is your complete AC system, you can say. The engineering challenges are there for the cabin acoustic, like whenever you want to design the cabin, how much the space is there, we have to rectify that particular space, and we have to use for quantifying the noise experience. Okay, so the person who is sitting in the inside the car, okay, it's not and then the outputs of it, okay, like reduce the sound power levels are there. Okay, and the other levels are also there, like vibration, and you can see like whenever we drive the car over the bumps. Okay, that suspension capability is also mentioned there. Okay, to not getting hurt to the passenger who is sitting inside the car. Then the crash and safety parameter is there, so that's why we use the seat belts and all to, like whenever the accident is there. Okay, so like the So that's why we use like the crash parameter, and that's why we use these sleep rings and also whenever we sit inside the vehicle. Then the ergonomics are also there. How beautifully you can arrange your ergonomics. Ergonomics means it is not like it's the arrangement of it. Okay, so it is the arrangement of the particular parameters, like the where is the position of your where is the position of your clutch and all those things. Okay, like whenever you see the speed on the car, how much it is. Okay, like this is the head-on display you can see. Okay, on that particular mirror you can see, or where the particular window is there, where you can see the actual speed of the vehicle. And then the chassis simulation in the chassis simulations, you can see how the structural parameters are there, crash and safety of the particular chassis. Okay, because this chassis is like a backbone of your vehicles. Okay, like you can say the base of your vehicle, which is the chassis. Okay, because whatever the parts are there, whatever the components are there in the electric vehicles, that particular components mounted on the chassis part only. Okay, like whether it is your brake, suspension, steering, or your complete external vehicle body is mounted on the chassis part, wheel or tires also, like shaft and engine, gearbox, motors, and all those things. Chassis structural capabilities you have to check. It is not like you have to check the structural capability. It is more structural capable. Okay, and it has also a less weight. Okay, it is not like it is not going to be failed because of the fatigue life. Fatigue life also you can check. Okay, like the repeatable stress is there, how much the peak stress value is going to be there, because of the bolted connections are also there. Sometimes the welded connection is there. Because of that connections, the stress value is going to be different. Okay, in the bolt it is different, in the welded part it is different. Then the crash and safety parameters again, brake and suspension part. In the brake part you have to check the how much the brake disc you need. Okay, and in the brake disc you can see, like in the bike you can see, like in that particular brake disc the holes are there. Okay, that holes are there because at this particular holes region na. Okay, first whenever we starting to design that particular brake disc, okay, it is like a solid part only. Okay, so whenever you analyze it, we can see like at this particular part there is no heat is there. Okay, or that much of heat is not there. Okay, so we'll remove that part and we'll use that part as for like a to dissipate the heat. Okay, to remove that part we gain the suppose the weight is less. Okay, and we will get the more thorough capability. Then the painting part is also there. Then the wheels and tires. Okay, like you have to design the wheels also and the tires also in a particular way. Like it is depend upon the vehicles, like which vehicles you can use. Okay, for the off-roading vehicles, the tire geometry is different, and for the highway vehicles, or you can say for the highway vehicles, it is different. It is based upon the condition, like how the environmental condition and how the road conditions are there. Based upon that, this tire is going to be designed. Then the multi-domain and powertrain analysis of it, multi-domain and the multi-physics simulation. Is the internal combustion engine, transmission, fuel system. So it is talking about only the like a hybrid electric vehicles. In the hybrid electric vehicles, that electric powertrain is also there, and the internal combustion engine is also. For the internal combustion engine, the Forte tool is there in the ANSYS. Okay, which you can use for the combustion efficiency, how much the fuel is going to be spread inside that engine part, or you can see inside the cylinder. Okay, that also you can check. Here you can see like inlet and exit hole is there. Then the transmission is there. In the electric vehicles, that electric e-transmission is there. Okay, like the e-gearbox you can say. How the power is going to be transferred from the engine to the shaft, or engine to the, you can say the obviously to the tire. Okay, or you can in the electric vehicles it is from the motor to the from the motor to the actual wheels. How the power is going to be transferred. This is controlled by this particular transmission system. And these are different type of transmission also, like manual transmission, automotive transmission, DCT is also there. Okay, dual clutch. And then the fuel systems. how the fuel system you can design. That is based upon like in the combustion engines, the we can say like this is the turbocharged engine or this is a supercharged engine. So this is the natural aspirated engine. So like this, the fuel systems are there, like how we can design your vehicles to spray the particular fluid inside the, or how we can design it. Okay, it is based upon the Indian strategies there. Okay, which are the Indian strategies to develop. And then the exhaust systems, the same way is there. How much exhaust you want to fluid pressure, fluid temperature is how much the pressure is there. That also you can see. And then the electric powertrain is there. In the electric powertrain, the more focus is on the electric machines part. Okay, you have to check the electromagnetics part here, thermal part, as well as the structural compatibility part also. It is okay, whichever the motor you are going to use. Okay, so all the parts of this motor, particularly the stator or the motor, stator is going to be, and the what the rotor teeth is there. Okay, so all the parts are going to be well settled at this particular physics, like for the electromagnetics, thermal, as well as the mechanical physics. Okay. And then the electrical part, which is the wiring and connectors, infotainment screens are there, ADAS systems, which is based upon the various sensors, radar sensor, lidar sensors are there. Then the antennas for communication part. Okay. And then the electrical reliability. Electrical reliability is more upon like a wiring harness, how much the wiring harness is there. That is based upon it. That is the infotainment screen. Okay. Here the PCB is going to be used, multi-layer PCBs are going to be used. Okay. And for that PCBs, you have to check how much the power integrity, signal integrity is there. That also you have to check. Then the ADAS systems are there. In the ADAS systems, the various sensors are there. That sensor collect the data and given to the particular controller. Okay. And that particular controller, for the ADAS controller, you can say that particular controller control the complete scenario of the ADAS vehicles. Then the antennas are there for the communication part. And then the electrical reliability is also there for the EMI and EMC testings. Okay. This is the proven simulation examples are there. Okay. Increasing productivity for the Ferrari is there. Then the engine capability. Then the engineers which designs the vehicles, reducing the weight by 56%. Okay. So you can use the different strategy for the electric vehicles or any of the vehicles you can take. You can use the different strategy to make your vehicles more optimized. Okay. And some of the learning platforms are also there. Okay. So whatever we see, which is like a overview presentation of it. Okay. Only the overview of the automotive industry, what ANSYS has and what ANSYS can do for the automotive vehicles. Okay. Then you will see some learning platforms are there in the ANSYS. The learning path is like a AIC curriculum is there. Okay, so AIC like a that also I will show you like the ANSYS innovation courses are there. Okay, that is the free courses are there. Then the premium courses are also there, and then some subscription based learning materials are also there. Okay, so whenever we do the okay, so at the last I will show you like how you can enroll those courses. Okay, these are free of cost courses, how you can enroll those courses also. Okay, so now if you have any doubt about this particular presentation, you can ask. Okay, so this is just the overview of it. Okay, now after that, what I can do, I will show you like one electric motor simulations. Okay, from start phase to the last phase. Okay, how you can do the simulation for the electric machine. Okay, that I will show you from designing it to check the thermal capability of it. Okay, so all the simulations I will show you. Do you have any doubt here up to this point?
If anybody has any question,
Any doubt
I
if you have, you
request
can ask.
yeah, you can please type it in chat box. Like, if anybody has any question, you can type it in chat box. At the end of the session, we'll answer to all the questions. Like,
Okay. Now we'll start for the actual workshop part. Okay. The screen is visible itself.
Yeah, screen is perfectly visible.
Okay, sure. And this is the workflow you can see, or this is the software window you can see, which is the ANSYS workbench is there. Okay, that also I will show you. Like this is the workbench 26R1. This is the ANSYS workbench, and inside that I will show you like how to couple the actual particular ANSYS Maxwells, which is used for the electric machine design, and then the ANSYS Fluent is there for the thermal calculation of an electric machines or any of the component you have. Okay, like any of the automotive components you can take. Like your heat exchanger is there. So you can design your heat exchanger, you can analyze your heat exchanger inside the ANSYS Fluent, okay, which is the fluid and the thermal solver is there. And the ANSYS Maxwell is the electromagnetic solver. In the electromagnetic, in the Maxwell itself, we'll see like how we can do the analysis of an electric machines from the starting from designing geometry to the how we can see the results. Okay, like all these parts I will show you. Okay. Edit it. So here I coupled both the scenario Maxwell and the Fluent, like whatever the results or whatever the losses I got from the Max, okay, like whatever the electromagnetic losses, that based on that electromagnetic losses, the temperature is going to be show here. Okay, first we will see like how the electromagnetic losses are there, how it is developed, and all those things we can see first. And then I will show you like whatever the electromagnetic losses are there, that electromagnetic losses is transferred, which is correct or not. Okay, so it is like those main thing is that whatever the losses is going to be transferred, okay, that should be transferred correctly. It is not like a random losses is going to be transferred though. So whatever the losses showing here inside the Maxwell's, particular that amount of losses only it is showing inside the, it will show inside the Fluent part also. Okay, it is just opening the ANSYS electronic desktop. This is the GUI you can see. This is the GUI of ANSYS Maxwell. Okay. It is an electromagnetic solver which is used for the design of an electric machines or any of the electrical component you have. Okay. You can use ANSYS Maxwell for the designing of an electric machine. Okay. That you can see this is the electric machine we have. Okay. And here the one thing you can notice here. Okay. So it is not like a complete electric vehicle is there. Okay. So it is the electric vehicles. Oh, sorry, the electric machine is there, but it is symmetrical in shape. And it is in the 2D part. Okay. Here you can see the Maxwell 2D. So this is the 2D electric machines which is symmetrical in shape and which is symmetrical around for the 45 degree. Like this is 90 degree and this is symmetrical around the 45 degree. And how we can do the analysis of it? First we have to do the, or first we have to draw the geometry. So geometry, you can use these tools. The draw tools are there inside the Maxwell. You can use those tools to draw the geometry, or you can import your direct geometry from any of the CAD softwares. Like if you have the any of the AutoCAD file or any of the Parasolid files or SolidWorks, NX files, you can directly import those step files there, okay, for the geometry, and then you can use your geometry and you can give the boundary conditions. Now, what are the boundary conditions? Are after importing the geometry, you need to specify the materials to each part. Okay, like this copper materials, like I will show you, these are the coils are there. These are the 6 coils are there. Okay. So that highlighted in the orange color, these are the 6 coils are there. This is the rotor section. This is the stator parts are there. This is the complete stator you have. Then this is the first magnet. This is the magnet second. The two magnets are getting used, which is are in the V shape. Okay, and then the shaft portion is there. This is a shaft which is made up of stainless steel. Okay, and then the band region we have and the complete region part. Region is like or the boundary, you can say. Inside that region only the Maxwell solves is Maxwell equations. Okay, whatever the Maxwell equation is there, that is going to be solved inside the particular region. And now first, if the electric machine is there, okay, we have to provide the speed parameter or the velocity to particular rotor part. Okay, like whatever the moving parts are there. So we provide the velocity to the moving parts. Okay, so which is actually its value is speed make. I think this is a 4000 divided by 3, which is around 1333 is the angular velocity that we are giving here. Okay, for the rotor part, stator and the magnets inside it. Okay, and that particular motion setup we given to the band region. Okay, so inside the Maxwells, we have to develop the band regions or we have to create the band regions. Okay, the band region is like a region. Inside that, whatever the components are there. Now here you can see the inside the band region, the shaft is okay, magnets are included. In particular three parts and motion diameter of which is a 1333. Okay. Then after that, the boundaries are also there. The boundaries are like, okay, so whenever we design the symmetrical machine, okay, so what Maxwell's can do, okay, okay, so Maxwell will calculate the results for the whole machine. Okay, so it is not like it will calculate the results for the half machine only. Okay, or the particular whatever the machine we design here. Okay, so you can create the symmetrical part here. Okay, but that symmetrical part you have to mention also. Like whenever you want the full model results, you can go to design setting and here you can mention the symmetrical part. Okay, like this is my machine. In the physical, my machine is full 360-degree. Okay, but right now in the simulation, okay, it is the 1/8 symmetry is there. So that's why you have to mention the 8. 8 means like this is the eighth part is there. Eighth part means 1/8 part. Okay, at the 45 degree, 45 multiplied by 8 you can say, which is around 360. Okay, so that you have to mention. Then in the results, you will get the results for the full machines. Okay, not for the half machines you will get. So in the simulations, why we use this symmetrical parts? Because to save the computational time, okay, and to save the hardware requirement also. Okay, because if you want to do the full machine analysis, it will require more simulation time as well as the more time it is required for the simulations, as well as the more hardware capability, like more advanced hardware capability also you have to use. And now when we use the symmetrical model, these two boundaries we have to assign master and slave. What is the requirement of these two boundaries? Okay, to like replicate the results. Like this is the 45-degree results. Maxwell replicate the results for another 45 degree, then another 45 degree, like the eighth part it will create in the result section. Then the excitations part, the phase A excitations, these are the phase B coils and these are the phase C coils are. These are three phase excitations we have given, which is the current excitations we have given that you can see. This is the equation. This is the equation we propose here for the current. You can give the voltage if you have the voltage value, you can give the voltage excitation, or you can give the external or PWM voltage excitation also. Here you can pick the solid or stranded winding. Okay. Stranded winding means it is like the strands are getting used for the wire part. Okay, and if the solid you selected, okay, so it seems like the only one solid material is there for that particular coil. Okay, it is not like the bundle of wires. It is only a one wire is considered, okay, which is solid in shape. So like this is a phase A, and here you can see cos multiplied by cos into 2 pi. This is the frequency, electrical frequency, fundamental frequency is there, time, and this gamma is there. Okay. Then for the phase B, gamma, again the phase advance is added here. Okay, for the phase B minus 120 degree, and then for the third phase also you can see the plus 120 degree. Okay. Means this is the phase starting from minus 120 to plus 20, plus 120. Minus 120 is, okay, this 120 plus 120 0, and this is within the plus 120. So it means the 120 degree phase difference is there. Okay, and after that excitations, okay, here the excitations are there. Okay. These are the two magnets we have. Okay, and for these magnets, okay, these are the magnets are there. We have to define the magnetization directions. Okay, like the magnet is there, that magnet has a south and north. Okay, so like that we have to assign the magnetization direction also in the materials itself. So this is our magnet material. So we'll see here the properties. Like I will show which is the magnetization value is there, which is the magnetic coercivity is there. Okay, that particular parameter property name is the magnetic coercivity, and here you have to assign the direction, like at which direction the magnetization is there. Okay, so based upon that it will calculate, software will automatically calculate which is your south and which is your north pole based upon that coercivity values. This is the magnetic coercivity. It has value as 894 times 0 ampere per meter, and it has the direction of x component. Okay, the x component which is towards the positive x. Positive x means that you can see this is the x direction. In the positive x directions, the magnetization is there. Means magnetization, suppose x direction is this one. Okay? So magnetization direction, magnetization vectors are there that should be pointed towards the x. Okay, this is the coordinate system we use also, like relative coordinate system, this one and this one also. Okay, for the each of the product. This is for the object 1 and this is for the object CS2. You can see. These directions means in this particular directions that magnetization vectors are there for the each of the geometry. This is for the magnet 1 and this is for the magnet 2. You can see this one is the direction. Okay. After that the mesh parameters are there. So whenever you use the mesh, okay, in the transient solver you have to give the mesh parameter. Okay, like this is the transient solver used. Instead of this, you can, for the whenever you want to give the motion conditions, okay, the only one option you have, which is the select the transient magnetic solver. Okay, it is also have a electric solvers also. You can use the electric solvers for the electric field calculations. Okay. Other than the transient magnetic, it has magnetostatic, which use the DC current as an excitation. Okay. And in the AC magnetic solvers, it is like a frequency dependent solver. So it is use the AC solvers, and you have to give the frequency value also, like at what particular adaptive frequency you want to use your particular product, like the wireless charging simulations you can do, or for the transformer parts also you can use the AC magnetic simulation parts. Okay. So whenever you want to do the simulation based upon the time, okay, so then you have only one option, select the transient, magnetic transient. I hope you understand this excitation phase. Okay, so after the excitation phase, this is the mesh parts are there. So in the mesh part, you just need to select the option, select the inner the geometry. Suppose this geometry is there, and you have to do the mesh on selection. On selection is a surface based, and this inside selection is a 3D mesh. So the analysis part, in the analysis part, you have to give the stop time as well as the time step. And here you can see the stop time value. This is stop time value. You can see we gave the value based upon the equations. Okay, 1 divided by fundamental frequency divided by 100. So the time it will calculate which is 0.0001125. And the time steps we are using for 0.5 divided by the electrical frequency, which is 0.005625. Okay, so you can directly assign the time also. Okay, it is not necessary to give the equation like this. You can directly use the time steps. You can directly use the stop time like this. Okay. Then the results. Okay, so after analyzing it, we can see the results. Okay, so for this much amount of time, we'll analyze it. Okay, now you can see the results. This is the torque results. Okay, and we calculate the average torque. Okay, here you can not calculate like how much the actual torque is there. Okay, so that's how we calculate the average torque, which comes around 97.2236, which is in Newton meter. Then the back EMF value. Here you can check the RMS value also for the each phase. So go for trace characteristics, all the RMS. To see it. Suppose RMS. Okay, don't calculate for the full. And here you can see the RMS value for the induced voltage for the each phase. Then the loss parameters you can see the core loss, AD current loss, excess loss, solid loss, stranded loss R, and stranded loss. Okay, these are like you can see this 1.4795. These are the winding losses you can consider because the stranded losses is there now, and the stranded will assign to the winding part. These are the stranded losses. The copper losses you can also consider. Hysteresis loss, this is the excess loss. These are the core losses of the stator and the rotor part. And then in the calculator expressions, you can calculate particular the losses at the stator part. Okay. So once we calculate these losses at the stator part, it will calculate at a depth of 100 or 1 meter. Okay. The 1 meter depth it is considered. The depth means like a stack length is there. Okay, whatever the stack length is there, because it is a 2D object. So software will calculate it is based upon it is multiply by the 1 meter. Okay, but whatever the depth or whatever the stack length you have, you can multiply to the particular value. Suppose you have a depth of 0.85 meter or 0.8 meter. Suppose. Okay, so you can multiply 0.205 into 0.85, and whatever the value comes, that particular value is considered as a losses of your stator. Okay, so it is like a calculation is there. And then the mesh plots also you can. Sorry. If you want to see the animation of it, you can see that animation also. I'll also show you that. Now you can see the mesh, and now I will show you the fields value. Suppose you want to see the net B. Okay. Now from this one, here you can see. This. These are the frames only it will calculate. Okay, you have to save the field. So I will save only the few frames are there, only the 13, 14 frames we save. That's why you can see here. Okay. So how the motor is moving, okay, the flux part, yeah, like the flux density is there, the flux density is going to be changed on the stator parts also. Okay, that you can see the animation. You can speed up the simulations also like this. Now you can see. Okay, and here you can see the time as well as the speed and the position of it. It means the position of your rotor part. Okay. Now based upon these losses we calculate here, and here also the losses we calculate. Now based upon these losses, we will calculate the thermal part. Okay, the thermal means how we can calculate the temperature of it. That also we can see. So if you have any doubt, anyone has any doubts in the Maxwell part, if you have any doubt in the Maxwell, you can ask. Okay. Now we will move towards the ANSYS fluent part. Okay. Now we'll open this fluent. Okay. Now one thing I will also show you. Here the losses you can see how much it is. 205, and the depth of this motor, the model setting. The depth of this motor which is around 8 83.8 mm. Okay, and this losses is considered based upon the meter part. Okay, so meter and mm which is like a 0.083. Okay, 0.083. 8 you can multiply this, which comes around this 206 multiply by, okay, which comes around the 17. Okay, the 17 watts are there. Okay, so now we will see in the fluent also like how much the losses is there. So whenever we calculate the losses, which loss comes around in Maxwell, which is around 17.26. Okay. I will also see whenever we transfer the losses, how much the losses is considered in the fluent also. That also we will see. Just open the fluent now. This is the ANSYS fluent. We just transfer these solutions. Okay, whatever the losses we transfer to this particular setup file, and here we will calculate. Okay, the fluent is opening. And ANSYS fluent you can use for the any of the thermal applications of for to check the thermal parameter, to check the temperature. You can use the ANSYS fluent. Just wait for the 2 minutes. It is opening. This is a 3D machine. Okay. So here we can see the 2D machine is there. Okay, but here what we can do, we'll import the 3D design of the machine. Okay, and whatever the losses we consider in the 2D. Okay, that losses will transfer here. Okay, I will see again. First, we will assign the energy equation. Okay, the energy equation is going to be solved. This is the solver in the, and then the energy equation means whenever the heat transfer problem is there, okay, so that energy equation should be on, which makes the calculation based upon the conductivity value. Okay, whatever the bulk conductivity is there, based upon that value, it will calculate the thermal property, like how much the temperature is there, how much the heat coefficient is there. So all those values it will calculate. Here you can see the energy equation is on, and here the basic equation like viscous standard K omega is getting K epsilon standard of option it is getting. You can use this K omega equations also. Okay, this is the more standard model. 3D models here, the windings parts are there. There are the winding part also you can see. Okay. Then the materials also I will show you. Materials we created cast iron, copper, insulation, solid air, and still we assign that particular material to the each part. Okay. Like this cast iron assigned to this particular. Like whenever you go to the display you can see the every part. There are the parts are there. Solid parts are there. Air gap, frame, insulate, magnets. One by one, if you want to see, this is only the solid air gap. This is the air gap region. And this is the frame. Or you can see like a housing, insulation. These are the insulation of the winding insulations. And inside that, the insulation, these are the magnets part. And these are the phase A, phase B, phase C. These are the coils are included here that you can see. And then the rotor part. This is the rotor. Shaft. Solid teeth. And then the yoke part. If you consider all of this, it will showcasing us the full geometry like this. Like this is the full geometry that we have here. Machine, rotor, stator, and all these parts. Okay. Then we assign the particular material to the particular component. Here in the cell zone conditions, you can see this solid air gap. So this solid air gap we consider we given that particular to the air, that you can see the air solid air we consider that material. In the frame, for the frame we give the cast iron material. For the insulation, we give the insulation. We created this material. So okay, this material is not available in the library, so you can create these materials here. Then for the magnet, solid magnet, we given the steel as a magnet material. You can use the different materials. Okay, no issue. Any of the material for this phases, these are the coils. We given here the copper material. Okay? And to assign the source term also. The source term is how much energy is there, how much the power, or you can see like the how much the heat is there. So it is calculating based upon the watt you can give, and it is calculating based upon the watt per meter cube. It will divide the volume of the particular which part, and it will divide into this. Okay. So whenever the heat is there, that heat is calculated in the fluent, which has a formula or unit you can say like watt per meter cube. Okay, means it is calculated based dividing the volume part. In the boundary conditions, we just given the boundary condition to the wall only. Periodic walls, they are the walls we have. The periodic walls. So for this, all the convection boundary condition we given there. Like here you can see wall, rotor, wall, magnet. So all this we given the boundary conditions. After giving the boundary condition, And from here, EM mapping option is there. When you go to the file, and here you can assign the volumetric energies. So once you suppose select it, okay, you have to select the energy source, solid, rotor, teeth, yoke. You will select, just click on OK. Once you click on OK, it will calculate the particular energy sources here. Yes. And it will show you. Once it is loaded, it will show that. Okay. Now you can see. Total loss is around 19.59 watt. Okay. Or the each part is there. Like this 14 point, you can see 14. This is 37 and this 31, which comes for the stator and rotor. And that you can see that we can do the total of it 14 point something it is, and this is 2.3 means 3, you can say 14 plus 3 17. 17 is considered as for the stator and the rotor parameter as we got here as around 17. Okay, which if we design to the particular depth, we get the value for the 17. The same value you can get here as like this 2.9. This is the stator, sorry, the stator and this rotor part. Okay, because we selected only the 4 parts for the EM mapping. Okay, that's why we given the in the sales zone conditions, we given this frame part. Sorry, this phase part we given the source value. Okay, because we are not calculating that source term from directly from the maxwells. We are giving here. Okay, so that's what we giving here the 2 6 times 0 to e to the power 6 watt per meter cube. Okay, this is the power source value we given here. And based upon this value, it will calculate the temperature. In the boundary conditions, because there is no source here, source means any of the cooling jacket or anything is not there. Only these are the ducts you can consider to the frame. It is used for the heat dissipation. And these are the report definitions. We will calculate the volume temperature also. How much the temperature is there for the coils part, that also we will see. Just run the calculation first. Okay. It won't take that much of time. I can see it calculate temperature for the which part, the coil, sorry, the coil part. Okay. And now you can see the scaled residual, you can see. This is the volumetric part. When the temperature is comes around of 378 in the Kelvin part. Okay. If you want to plot the graphics also, if you want to see, you can just go to the contours to temperature and display, and that you can see. If you want to see that in the Celsius, you can just change the unit of the temperature. Temperature to suppose Celsius. Okay. Here you can't change directly. Now you can see here the temperature. Okay. Once you again plot it, save and display. Now you can see this value is going to be changing. And here this values also you can change. Precision more you want, not exponential, just a general value. Apply it, and now you can see. Like this values also you can. Static temperature from 66 to 133, and 113 is around at the like whenever we expect. Like we expect the more temperature at the winding part. The temperature is more at the winding part of the, and at the outer region, or you can say like the outer part or the housing part. which has a less temperature. And at the shaft also you can see the temperature. Okay, like this you can plot the temperature value. If you want, you can add the cooling jacket also. The cooling jacket means you can add the cooling part here. That examples also I will show you that cooling part example. So this example, this is the same type of example is there. It includes that cooling jacket part. That also I will show you. Once it is open, cooling jacket. Oh, this is the water jacket is. The water jacket I will show you. Means you can use the water jacket also for the cooling part and see like how much the difference is there in the temperature. Okay. Obviously, whenever you add the cooling jacket or the water jacket, the temperature is going to be low. Or you can change the insulation techniques or all these things also. It will depend on like which parameters and which materials you are going to use there, which type of components you are going to use for the cooling part. The same type of machine is there. Same type of machine. Just calculate it. It's the outer temperature graph is there. I'll show you the plot. Temperature if you want to see. Okay, all the parts, the water jacket. This is the water jacket geometry you can see. Now you can see. This is the water jacket geometry, and at this particular water jacket, how much the temperature is there. Inlet and the outlet point also, how much the temperature is there, that also you can see. In the report definitions, magnet average temperature, water outlet temperature. How much the water outlet temperature is there? It's around 306 Kelvin. This is suppose in output that show you in the complete geometry. Now you can see. This is the water jacket input, and this is the water jacket output. That you can see the arrow also, it will indicate that. In this is the input and the output also I will show you this. So this is the input, and this is the output of the water jacket. and the other values are is so based upon these two values, it will calculate the this is the magnet average temperature. Also, you can calculate. So you can plot the any of the values here. If you want to plot the path lines, that also you can do that. Path lines or suppose vectors. Temperature values you can calculate. So it is like based upon the what is the temperature value is there. For that only this fluent is getting it. You can add the multiple designs here also, and based upon the design also you can check whether your design meet that particular temperature value or not. So like this, you can use the ANSYS Fluent and ANSYS Maxwell for the for calculations of the electric machine temperatures. Okay. So up to this point, if you have any doubts, you can ask like any of the doubts regarding the Maxwell and regarding the Fluent part. If you have any, are free to ask.
I think Mr. Ramesh Ram Mangesh has a doubt, and even Ashwini Pawar. They have typed in chat box.
Assignment. Yeah, with ANSYS, you can reduce the losses also. Like for the reduction of losses, you have to use the different techniques. Like whenever you choose the solid windings, you may get the more loss value. Okay. And whenever you choose the actual standard winding, like in the transformer case or in the motor case also, you will get the less value based upon like the two different winding connections are the standard and the solid. So my option is like you can prefer mostly the standard windings because in the real applications also, like in the physical setups, the standard winding is mostly here. Okay. You can't see any of the machine is there or any of the applications which has used the solid wires, okay, like the bunch of solid wires, or only the one solid wire is getting used instead of a bunch. Mostly the standard wires are getting used, the standard wires making the bunch of each other, and that particular wire is going to be used in any of the application is there. Okay. Mesh assignment, like how can I help you with the mesh assignment? Like, can ask any of
Like,
the questions.
can I ask?
Like in the mesh,
Hello, sir.
yeah, you can ask.
Yeah, like while assigning mesh assignment, we have to uh, assign mesh for every geometry like stator, rotor, magnet, and like that. All particular
Yeah,
geometry setup.
yeah, sir. You can asking in the Maxwell part, or you are asking in the Fluent part.
The Maxwell board, sir, right?
You are asking in the Maxwell itself, no?
Yes, sir. Right.
Yeah, you can give the mesh part to the each of the geometry. Whenever you use the transient simulation, na. Okay, so that time it is
Okay.
necessary, or you can say like a recommendation. Like you can
Uh,
use the this transient alone because that whatever the time is mentioned, okay, that time is mostly affect the FEA mesh. Okay, so that's why we recommend to
okay.
all the transient simulations to give the mesh parameters from your side itself. So in the electric
Okay.
machine case, that air gap mesh is most important.
Yeah.
If the flux is not accurate at this air gap, the air gap flux is not accurate, then whatever the losses or whatever the flux density you will get is mostly incorrect.
Oh.
Okay. So so for that you can give the mesh whenever you are doing the transient calculations.
Okay. Yeah, I
Like
know.
for
For
the
the
other
electromagnetic,
calculations, don't worry about the mesh parameter.
yeah, that adaptive mesh will come on.
Yeah, yeah, right. You can use based upon the which solvers you are going to use, and you can give the mesh parameters.
Yeah, like if you are using symmetric method, right? Like doing, you will get the full
Mm-hmm.
efficiency. Uh, like we are using like 3D and full geometry, you get the full efficiency. Like in that symmetry 1/8,
The
1/4, you get the full efficiency of that
efficiency,
motor.
full efficiency, the whatever the results you got now, like you are simulating
Ah,
for the half geometry or any of the symmetrical geometry or the full models, you will get the
okay.
same results. Same
Ah,
results
okay.
means you will get the full results for the full machine only. Okay,
Ah,
but it
okay,
is
okay, okay.
like different whenever you are going for the non-linear analysis. That non-linear graph is
Ah,
not like the straight linear graph. Like
ah,
it is
okay.
going to be distracted towards in the middle of it is going to be like down or it is going to be upper side. Okay.
Ah, okay.
So whenever you do the 3D
So,
calculations and you do the 2D calculations, like whenever you compare those results, okay,
ah, okay.
so you will get the more approximate same results. Okay? So it's like
Yeah,
the
yeah, like,
99 or 9, whole 95% results are same, but the 5% or 3,
yeah,
2 to 3% error is there. Means you
yeah, okay.
will get the more
So
accurate results
before
in the
this, I
3D
have
itself.
used
But
ANSYS motor
what happened
CAD.
with 3D?
Can I
Mm-hmm.
speak, sir? Before that, I had used ANSYS
Yeah,
motor CAD.
motor CAD is for the 2D parts only.
2D part. Then after that,
Mm-hmm.
I convert that to 3D and then the 3D analysis also. Okay, but
Yeah,
that
you can
time,
do that. It's the
I
most
came to know
beneficial for you.
that from the 2D to 3D, it will get more 90% to 100% efficient. You get more accurate result. You will get like that. Right? So which one is better, 2D
Yeah,
or
in the
3D?
3D you will get more because this
More
3D
accurate result,
geometry
right?
represents your actual physical phenomenon now.
Yeah. Okay. So
As
like
compared
another
to the
one.
2D, you are
Okay.
whenever you build any of the motor. Yes, sir.
So okay, comes next question.
Okay.
So like that
Where in which
geometry
ANSYS platform?
for the hello, sir?
Yeah, you can ask.
Yeah. So like boundary assignment is there. Okay. But if you are using symmetry, the boundary is
Mm-hmm.
necessary. But if you are not using any symmetry like that, whether you have to give boundaries.
No, no, you don't need to give the boundary. Just you can give in the motor cases, you can give the vector potential boundary. Okay.
Okay, okay, sir.
So it is not like a necessary boundary is there because you have to make the solution uniqueness. Means you have
Oh,
to, sorry, not uniqueness. We have to make the solution unique to get the
okay.
more accurate results. Okay.
Oh,
Accuracy is not that much affected. Okay. But it is like a best practices methods are there now. So you can give whenever you are using the full geometry, you can give the like vector potential boundary to the outer region. Means the whatever the
oh,
outer boundary is there for
okay.
your machine, you can give to that edge of that particular phase if in 3D.
Okay. Then another one question, sir. Like some materials we have to add now. Like if you are going to use PCB stator like that thing, so you have to add that F1 in the library. How to add like
Mm-hmm.
that? You have to add you have to add the
Yeah,
material in the library, right?
yeah, you have to add the materials in the library. Okay, but
Uh,
for that library now, you first
uh,
need the properties of that materials. Okay, if the materials are not available, whatever the material you want to use, if that is
so,
not available in the library, you should know like how the properties are there, like how much the property, like how much the permeability is there. If it is a magnet, how much the coercivity value is there. Okay, that you should know. Then you can create the materials
okay.
like here.
Okay, sir. Okay.
Just go to tools, edit libraries, and then in the materials page.
Yeah.
And here you can add material, then you can create your own material.
Okay, sir.
But that material should be validated. It's not like a random properties you can give. Okay, you have to pick
Yeah.
the
Okay.
property like relative permeability. If it is
From the data sheet, you
P
have to
into
get.
H is your constant value, you can give the simple. If you have
Okay,
the
sir.
non-linear, you can select the non-linears and you can provide the BH curve data
Okay.
also. Yeah. So like this, you have to create and then you can validate the material here.
Okay, sir.
If you need to validate the material, if it is validated, then you can use it. Okay.
Okay.